So my name is Intan Nurhati. I'm actually a climate scientist at RCO, or Research Center for Oceanography of LIPI, or the Indonesian Institute of Sciences. So today I'm going to talk to you, discuss and perhaps review as well about the state of our oceans when we look at it from the climate change perspective. So I'm sure all of you have heard about climate change. Sometimes we refer it as global warming, but climate change is actually a better term because what we see right now is not just warming, but there are other things that are happening other than warming that is due to climate change. And I'm sure that all of you have also heard the culprit, the cause of climate change that we are experiencing right now. So that will be the greenhouse gas or consumptions of fossil fuel. But what I wanna go through with you is actually go through the physics of climate change and where is actually greenhouse gas takes place in this whole story. So here we are on Earth, our planet. We actually receive energy from the sun, solar radiations. And that is sort of the main driver of our climate system on our planet today. So the energy from the sun actually is in the forms of electromagnetic radiations, and it comes through space and arrive at the surface of our atmosphere. Some get reflected, but most get absorbed, enters our planet, and again at the surface of our planet, some get scattered on the cloud, but then some get re-radiated. So my point is this: if you remember your high school course about electromagnetic radiations, there's a spectrum of it. So there's a microwave radiations, there's UV light, UV, and infrared. And with this energy that we receive from the sun, essentially, when it comes, it's in the form of shortwave radiations, but when it's get re-radiated by our planets, it's in the forms of long wave radiations. Okay, so it's shortwave coming and longer wave going out from our planet. So what does that mean? So the greenhouse gas, such as CO2, water vapor, methane, they act as a blanket to our planet. So they are actually transparent to the incoming shortwave radiations, but they trap the long wave radiations. So we have incoming of energy, but then it gets trapped by the greenhouse gas. So now if we just take one of the examples of greenhouse gas, perhaps the most popular one, which is carbon dioxide, CO2. CO2 is a greenhouse gas that have a role in warming our planet. Oh, before that, I actually want to step back. So perhaps all of us only heard greenhouse gas in a back kind of story. Okay, a greenhouse gas is the culprit of our climate change and etc. But I also want to remind you, without greenhouse gas, actually the temperature of our planet is only minus 16 degrees Celsius. It's freezing. So without greenhouse gas, we actually cannot sustain the life that we see now. It's very important. But what happened right now is that we have an overdose of greenhouse gas. So what we observe right now is plus 15 degrees Celsius as average of our planet, and it keeps rising. And so this greenhouse gas that used to be very important now has become kind of attacking us back. Now, let's think about greenhouse gas and how it flows through different parts or reservoirs of our planet. So we have atmosphere, we have oceans, and we have lithosphere. Lithosphere is rock formations. Carbon goes through all this process. So it gets released from the rocks into the atmosphere through volcanoes. So volcanoes spew a lot of CO2, and then they get into the atmosphere. But eventually they will be absorbed by the oceans, and then that takes 1,000 years of processes, and then they become rocks or become lithified, and that takes like geological timescale, like million years. So here's the reservoir. The carbon goes through the cycle, but the resident times is different. The atmosphere is very short, and then the ocean, and etc. What's happening right now is that we have increased this CO2 outgassing, but not due to volcanoes, now due to our cars, our industry, and etc. And we have this part getting so much higher, but the way it's being absorbed to the oceans and into rocks is still the same processes. So what happened is we have these accumulations of CO2 in the atmosphere that we cannot absorb back into the cycle. Now you might heard this idea, the geoengineering idea, where we can actually capture CO2 from the atmosphere into the rocks, right? You probably heard of this geoengineering idea. And as it is logically very intuitive, if you understand this, if now we understand the carbon cycle, it actually takes so much energy to do that, so to capture CO2 in the atmosphere and make it rocks. So as it is now, it's very economically not so feasible to do that. So we end up with the situations where what we're doing right now is keep accumulating CO2 in the atmosphere and waiting to be absorbed by the ocean and under rocks. Our Earth is actually very old. It's 4.5 billion years old. It's seen many events. It's seen mass extinction. It has observed climate changes before. But what's unique about this time is how fast it is rising. And this is the statement from the IPCC. IPCC is the Intergovernmental Panel on Climate Change. So they update our status of our climate change. And they basically say that the atmospheric concentrations of carbon dioxide, methane, nitrous oxide, those are greenhouse gases, is unprecedented in the last 800,000 years. So humans are newcomers to this planet, but we are changing it in something so different that the old Earth has never seen it before. So if you, a climate scientist, there's also a lot of debate between climate change and climate skeptics, right? There's sort of these two back and forth skeptics, but there's actually a consensus, scientific consensus, that the ongoing climate change right now is due to human. And I thought this figures is the one that best display it. So this is the figures of temperature rise in our planet, both in the land and the ocean surface. Now the black line is what we observe. So this is the amount of temperature rise in our planet that is really happening, the black one. Now we can simulate this. Now what you see in the the blue area is the simulations of temperature if we only have natural forcing, if there is no human addition to it. And obviously we will have temperatures much lower than what we observe right now. Only when we simulate natural forcing and anthropogenic forcing that we get the pink line, which is very much the same as what we observe. So what's happening on our planet today, the risings of the temperatures, is only can happen because we are here, humans are here, and we have been driving it to that level. Now, as I say, the word climate change is a better term than global warming because the footprints of climate change is very multidimensional. It's not just our planet is warming, but the sea level is rising, and our oceans is becoming acidic. There are more stronger extreme events, and we are actually losing oxygens in our oceans. So I'm going to go through all these things. I know you probably heard some of these terms as well and understand it. Okay, what is sea level rise? In Jakarta, we are like quite low level. We actually already under sea level, right? So this is an issue when we have even higher sea level. Now, the sea level is rising because of two things. One is the thermal expansions. If you remember like junior high course, any material, if you heat it up, the volume will expand. That's the same with water. So as our ocean is warming, the volumes will go up. And the second one is due to the glacier and ice melt. So as the planet warms, a lot of ice, especially at the poles, will basically run into the oceans, and that as a whole increase the volume, and it makes it danger for coastal area. So where are we right now? Well, the IPCC say in the last century, we have about sea level rise almost 0.2 meters. 0.2 meters in 1 century. That's last century. How about next century? Well, next century is not really good. Even under low emissions, we're expecting about 0.3 to 0.6. High emissions, almost 1 meter. Some climate scientists actually think the IPCC estimates on sea levels tends to be conservative. What that means is they tend to be lower than what it would be. So some scientists say it could be as much as 2 meters high. So why it's so different? It was only 0.3 meters last century. Why it's almost 2 meters in the next century? Because sea level rise is one of those slippery slope issue. So you can imagine this is Antarctica. We have glaciation, right? You have glacier, and once you hit the ice, what happens is the ice becomes water, and the water will go through the cracks of the ice, and actually becomes lubrication. It lubricates the ice, so it will run faster to the oceans. So it's not a steady linear process. It's a whoosh kind of process. It gets faster and faster. And of course, once you chunk off parts of the ice that is in front of it, once that's gone, the rest of the ice will just run into the ocean. So that's why it is a slippery slope. And yeah, climate scientists have underestimated these issues before. So it's something to watch out. So I did mention 2 meters by the end of this century. Well, what is 2 meters like? In Indonesia, a lot of coastal area will be gone. In Japan as well, and the rest of the world. Now if you click further, now in Indonesia we have the most populated island in Java. So with the 2 meters sea level rise, a lot of areas in the northern part, Jakarta, Cirebon, Semarang, will be affected a lot more. And if we focus on Jakarta, that much Bekasi is also, Tangerang is also affected. But I want to hold our horse now. Don't blame everything to climate change. Not everything is to climate change. Especially in Indonesia, we are doing something else. We are taking our groundwater, and that is causing subsidence. And the level of subsidence is much, almost 4 or 5 times higher than the sea level rise from climate change. So I just tried these simulations. Basically, the yellow one is how much sea level do climate change, but the red line is due to subsidence from groundwater use. So we have to understand climate change as complex as it is, and then mix it with the societal complex. All right, let's talk about other imprints of climate change. We are losing our oxygens in the oceans. So you know when in the morning you make your coffee, you heat up your pot and it starts bubbling. So the gas start escaping from your pot of water. Same thing with the oceans. So as our ocean is getting warmer, oxygen is becoming less soluble. It's escaping the oceans. And we start seeing this as an issue. It's a slow kind of issues, but what you see here is where places on Earth that will start to be hit by this oxygen missing or deoxygenation issue. Another thing that we have to watch out is oceans becoming acidic. So this called ocean acidifications, sometimes refer to this the evil twins of global warming. So what you see is on the red curve, as the concentrations of CO2 increase in the atmosphere, our pH in the oceans goes down because it goes back to that global carbon cycle. And indeed, we see actually about 30% of our emitted carbon dioxide has been absorbed by the oceans, and corresponding to 26 increase in acidity. So what if oceans becoming more acidic? Well, our oceans have many marine organisms, and some of them are made of shells. Coral Reef have carbonate rocks, foraminifers, and so on and so on. So when our oceans becoming more acidic, many organisms that needs calcium carbonate, kapur, right, in Indonesians, will be suffering most as they cannot be living as they used to be. Another thing is extreme events. As we warm our climate, we put more energy to our climate as it's become more erratic. Now, we heard about typhoon in Japan, hurricane in the US. What scientists have projected, even when I was in grad school, I remember, is that as we warm the climate, typhoon and hurricane with higher category, so they have 1, 2, 3, 4, 5, 5 being the strongest. So those category 4 and 5 will be becoming more frequent. So more energy, we're building bigger typhoon. Indonesia, fortunately, is a bit okay from this, but our neighbors, such as the Philippines, they are very prone to typhoon. So their climate change adaptations will really have to take into place this issue. Okay, so I was lying about my title. It's not trouble, because it's not just warming and more acidic oceans. We have sea level rising, more stronger typhoon. The oxygen is missing, so it will be more troubles of our oceans. So that's the first part. We've talked about the anthropogenic climate change and what will be the footprints to our oceans. But I want to also go through with you the natural beats of our ocean. When we talk about climate, people always think about anthropogenic, human. But climate is so complex. It has its own beats. It has its natural variations that we need to understand. All right, the beats of our climate. Here in Indonesia, it's always hot. It's just wet or dry, right? And that happens on seasonal time scale. So here in Java, let's put it so simplistically, we have, let's say, 6 months of dry and 6 months of wetter conditions. But Indonesia itself is actually very complex. If you go to maybe Kalimantan, anywhere close to the equator is different than that. So instead of kind of having one peak of rainy season and one peak of drought, it kind of have double peaks because the sun crossed the equator. And if you go to Maluku, it's the craziest climate because they kind of have their own climate. So if you remember the orogenic process, so there's this process. If you have oceans and mountains, it will pull up water as clouds in the mountains. So in Maluku, we have a lot of big islands with big mountains, and they kind of have their own rain patterns, which is very different what is happening in Java, for example. This rainy and dry seasons happens annually, right? Seasonally. Now let's stretch it longer. On interannual, between year cycle, every 2 to 7 years, here in our planet, we have natural climate variability called the ENSO. ENSO is short for El Niño Southern Oscillations. All right, it occurs 2 to 7 years. ENSO has two sides. One is El Niño, and the other one is La Niña. How so? So this is what Pacific looks like when there's no ENSO. We have winds blowing from the east to the west, and you can imagine this is the equator. So it accumulates a lot of warm water in Western Pacific, and you have ocean upwelling in the east. So that's why Indonesia is wet. Indonesia, Southeast Asia is wet because we have this hot water near our area, and we have like your coffee pot. When you have hot water, you have rising atmosphere. So that's when there is no ENSO. Now what happened during El Niño? You can click. During El Niño, you have essentially this trade wind is weakened, and so the hot water in the Western Pacific spills towards the east. Now, if your coffee pot is in the Central Pacific, so is your rain. So if you remember, like during El Niño, actually we have dry conditions. The 97, 2014, etc. And there's a lot more ENSO. So this is during El Niño, one side of ENSO, and what happened during the other side of ENSO. And if you can click, now it's called La Niña. La Niña is super normal, so the winds is very strong. You have even warmer temperature in the Western Pacific. So for Indonesia, we get even wetter condition. So we have more rain in Indonesia and even less rain, let's say, in Peru. So this happens 2 to 7 years. Some ENSO stronger than the other, of course. And so we got the seasonal, now we got the interannual. And this is, again, natural climate variations. And now go even further. There is natural climate variations that go up and down every 20, 30 years. A good example of this is the Pacific Decadal Oscillations, or the PDO. So this story actually was invented by the fishermen. Fishermen in South America, they were catching sardines. They were catching it until at some point they couldn't find more sardines. So they say, oh, it's an overfishing issue. We fish too many sardines, there's no more left. Where it's like actually part of a climate system. So in the Pacific, there is a regime of PDO, the positive part of PDO, when the ocean is warmer. And then during the negative phase of PDO is colder. And the fish just follow them. So when it's warm, sardines, who likes warm water, will be there, right? But when it's colder, anchovies will follow the cold water. So what happened was not because they were overfishing, but because the sardine, we just don't like the cold water, and now it's time for anchovy. So it's very important actually to understand this. And I think for people in the fisheries community, again, you cannot blame some things too quickly. All right, so we have the seasonal, we have the interannual, now we have decadal. There's even more. There's even longer than that. Any of you have heard about the Milankovitch Cycle here? No? Okay, great. So my first slide was talking about how we get our energy from the sun, which means what happened to the constellation between the Earth and the sun will affect our climate. Now, we know that our climate rotates around the sun, right? Well, the way they rotate, the way their positions actually changes. Now, this is a kind of hard terms to say. So the Milankovitch cycles has 3 components: eccentricity, obliquity, and precisions. So what is eccentricity? Well, we know our Earth rotates around the sun, and the orbit is not a perfect circular, it's actually elliptical. But do you know that the elliptical sometimes is stretched further, sometimes is more orbital? And this happens to our planet. So basically for example, when you have this brown one is more circular, and some point it will be more elliptical, like the orange orbit. What does it mean to our climate is that our planet encounters more variations in solar energy when we have this more elongated, like this orange type of orbit. And this have a cycle, 100,000 cycle, 100,000 years of periodicity. Just because the way our climate and other planets works. The second components of the Milankovitch cycle, so Milankovitch was a geophysicist and astronomer at the same time, that's why he thought about this, was the obliquity. So now I remember, I think when I was in middle school, my teacher told me that, oh, the Earth is not straight, it's tilted. And I think he said 23.5 degree. It's actually not entirely true. I can say that it actually varies between 22.2 and 24.5. And when it's tilted, going back and forth, it has a cycle too, and it's 41,000 year cycle. So that, of course, affects our climate in the way how much solar radiations is received at the poles. All right, next. The third and the last part of the Milankovitch cycle is precessions. So our Earth is wobbles, it's not really stable, and this affects how the tilt and eccentricity and how much solar radiation we receive. And the cycle is 19 to 23,000 years. So the beats of our climate is not just the rainy and the dry season, it's something that happens beyond a lifetime. So basically when you combine this precession, obliquity, eccentricity, you have this fluctuations, right? And scientists think that this 100,000-year cycle, 23,000, 41,000 cycles, has something to do with the glaciation cycle, so with the ice age. But the truth is more complex to that, the way how this affects the glaciation. So glaciations have kind of cycles of 100,000 years, and they kind of have these small cycles of 41,000 years. So they're there. All right, so with that, we've covered the natural beats of our solar system. On seasonal in Indonesia, at least we have monsoon. On interannual, we have ENSO. I didn't talk about the Indian Ocean Dipole, but it's another interannual, but centered in the Indian Oceans. And actually, if you go to the Atlantic, there's so many other oscillations. It kind of gets overwhelming sometimes. On geological timescales, you have the Milankovitch Cycle. So what? So the point is this. If we want to understand how much human contributing actually have footprint in our planet, we really have to have a really good understanding of these natural beats, right? Because naturally climates go up and down, and where we are in terms of this. And we also have to have very long data. You can imagine, if you say, oh, the climate change is due to human, and you only have 5 years of data. 5 years. While we know that the PDO is 20 to 30 years. So it may well be that the rising in your temperature is just part of PDO. It's nothing human. So that's why you need to understand and get longer data set. So how do we observe our oceans? How do we get all this data? Well, we've been very creative about this. So we did it from the space. So since early 1980s, we start to have satellite rotating around our Earth. And satellites are great. We can get sea surface temperature from everywhere on Earth. And we keep getting this monthly data, right? So we get data from satellite, not only temperature, we can get salinity, we can look at the altimetry or sea level rise. We can monitor sea level rise using satellite. And if you don't use satellite, you can also use planes to some extent, maybe to study remote sensings, the color of the oceans, productivity, and so on. Now, at LIPI, for example, we have the research vessels of Barunajaya 8, and Barunajaya has also been observing our oceans. So we go on cruises, and then we lower down our equipment so we can tell what's the temperature and other parameters, and we also grab water samples to study in the lab. Some people put buoys. Buoys is when you put instrument in one place. It's a buoy, so it's attached to the ground, so you can have data from the same place all the time. As opposed to ships, when we go on cruise, we only go there at one point in time and then we leave, but buoy stays there. And there's also Argo floats. Argo floats is this autonomous submersible. So it is an instruments that go on the surface and then go down, dive deep into the oceans, and it will be recording a lot of information, and it will go up, and then it will send its signals to the satellite. So this is also a nice way to monitor our oceans. Another thing, so this is like sort of in the field, right? But being an oceanographer, you don't have to be always a field person. You can be a computer geek, actually. There, someone's smiling. Or organizers, actually, a computer modelers. So what you can do you can do a lot with ocean models. So you model the oceans, how it's going to be in the future. And that's sort of the sexy part of models is you're not just talking about today, you're talking about what's going to happen after today. Now, this is the whole data that we need, but as I highlighted in my previous sections, we need a very long data. Now, if you think about it, how much data have we got from all this combined? Satellite has only been around since early 1980s. So from 1980s to now, we have good coverage of data. But what happened after that? And we know that we need a longer data sets to really understand our climate. So if we haven't measured our surrounding, and we already passed the time, we don't know what happened in the past, we could ask nature. Nature have these informations. And this is what we call natural archive. So many of you, I'm sure, know about rings in the trees, right? In the barks of the trees. So every year it has marks of its rings, and you can count the rings. You can tell maybe if the ring is the space is very small, maybe there's a drought. Maybe it was suffering, that's why it doesn't grow as fast. Now these 3 rings also apply in the oceans, but maybe just not many people know it yet. It's in the Coral Reef. So in Indonesia, we call Coral Reef batu karang. So we think it's batu, we think it's stone, rocks, nothing living. But it's actually a living thing. It's actually animals that collaborate with plants. And so corals like this, they used to be small, and then they grow bigger and bigger. But the way they grow is they secrete calcium carbonate, so the kapur kind of materials, keep bigger and bigger and bigger and bigger. And when they were building these materials, they're making rings. So if I drill these corals and I put it in the lab, what I see is rings of seasonal change. So I can, if I, let's say, take the samples in 2018, I can see what happened in 2017, 16, 15, and so on and so on. So this is our archive. This is our history book of our oceans. If we didn't measure anything before, we can ask them what happened in the past. Now using this, I can tell a lot about temperature, about climate change in the rainfall, pollutions, as well as the health of the reef. So if you click, so this is basically how the process looks like. We find big corals, and you drill it, and then you have to retrieve the core, and voila, that's our record. That's our history book of our ocean. Okay, now we have these materials. What we do about it? What we do with it is we measure chemical things that is embedded on this. So if you click on this, okay, so all right, the video is working. So let's suppose we want to have reconstructions of temperature. What you get from satellite is the black curve. Like I say, satellite only starts in 1980s. What happened after that, there's no information, right? Very sparse informations. But with Coral Reef, you can extend those informations, and we can actually go back to last century and before. So here's our climate archive. We not only have coral cores, so with coral I can go back to 200, 300 years, and very nice resolution data. I can study El Nino, for example. But we can also use deep sea sediment. So when we go on Barunajaya, we can core the sediments of our oceans, and they also have layers. And with this, we can actually go to tens or even 100,000 years if we get lucky. So how did we know what happened during the glaciation time? That was through the sediment. And so with this climate archive, basically what we need to find is anything that has layers. And one of them actually is also ice core. Ice core, when you have snow, you deposit the ice, and then it will record a lot of things about the surrounding, and it becomes layers of ice. And you can study climate through that. Now, when I say ice core in Indonesia, really? Yes, we do have ice cores. Jaya Wijaya. Scientists actually have gone there and core the ice in Jaya Wijaya to study our climate. Although, sort of the sad story is that due to the climate change, the ice has been melting a lot, so that the record from ice core in Indonesia has become less reliable or has some issues with it that we need to solve. It's not like a clean core, like if you go to South Pole or on the South Pole particularly. So yes, we do have all this range of climate information that we can dig. Alright, so that's what we learned today. We talk about anthropogenic climate change, which I'm sure many of you is most familiar, heard a lot in the newspaper and whatnot. But again, you need to understand the natural beats of our climate systems. And all of this makes us realize the importance of climate data, that we have to monitor and study our climate. Not only today, keep measuring, or Corey with her climate simulations to the future, but all of these present and future tools needs to be calibrated by longer time series from the past. So with that, I thank you for your attention.